All right, so looking at 22.2, exponential decay. Learning targets for today: describe characteristics of exponential decay functions and graph and analyze exponential decay functions. So for number 1, 2, and 3, well, for this section, we're looking at half-life. So we're looking at radon. And for number 1, what is the amount of the radon in the house 4 days after the source was eliminated? Explain your reasoning. Jordan, do you want to come up and put number 1 up, please? Okay, so you're going to do number 2. And then Shannon, you're going to do number 3. And here's some stickers. Right, so number 1, multiply by 1/2 because we said that the half-life was 4 days. So after 4 days, we have half the amount left. So we have 200 keys. I don't know. Anyway, so compute the difference. So difference is the keyword that means subtract. So 400 minus 200 is 200. And then determine the ratio of the amount of radon on day 4 to the amount of radon on day 0. So what we have is what we started with. So we have 1 to 2. So on day 200, we have 200 compared to the 400 that we started with. So when we reduce that, we get a 1 to 2 ratio. All right. How do we feel so far? Alrighty. So now we're going to look at the next. Wait till we get the table filled in. No, I'm not wrong. No, it's wrong. You're wrong. You're like wrong. Why? Oh, that's wrong. So wrong. Enough. You're Brad. No. Wait. 1 to 2. Oh, that's 2 to 2. No, on that. That's okay. How do you put times 2? X2. Say that again? I just put X2. That's a big name. Okay.
That one is wanders off.
Wait, times 2 or?
Yeah. Until we have a conversation, I think we.
You want me to write both ways?
Yeah.
No. But like, what do you get year to year? What are you doing?
Divide. Why did I do that? My life is great today. There.
You guys probably crew.
I just did my life today.
All right, so in our table, we're going from days after. So 1 half-life is 4 days, 2 half-life is 8 days, 3 half-lives is 12 days. So for each half-life, we're decreasing by half. So from 400 to 200, we're multiplying by 1/2, and then 200 to 100 times 1/2, 100 to 50 times 1/2. So we'll notice the difference here. Since we're decreasing by half, we're subtracting that amount, and then our ratio is 1/2 each time. So each time we're dividing by 2 or multiplying by 1/2. And so then, probably you're doing the graph.
Yeah.
So looking at the graph, and with this, we're just kind of helping to determine our ratio, if it's linear, nonlinear.
Perfect. 150.
Whatever.
Oh, whoopsie daisy. Cool, that's not necessary.
All right, so looking at this graph, is it linear? Do we have a straight line? Obviously not.
That's a good job.
And as Ellie points out, it does not have a constant slope. It's not increasing by the same amount. So it is not a line. All right, so questions on 1 through 7. Super duper. 8. Cole, you're going to do number 8. Tom, you're going to do number 9.
Yeah, it is.
So Renee needs to know the concentration of radon in the house after 20 days. How many radon half-lives are in 20 days? All right, so 12 and a half PCI
Have 5
and
half-lives.
5 half-lives
Why?
per liter.
He doesn't believe in connecting sides.
Yeah, connecting sides is
Yeah,
dumb.
basically.
It's really lucky, dude.
Oh my.
Fine. It's live, so it can't be half-lives. 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 Okay.
All right, and so how many radon half-lives are in 22 days? So if 20 days
Oh, how many
is
radon
5.
half-lives?
So if
Oh, okay.
if 20 days is 5 half-lives, and 1 half-life is 4 days.
It's 5.
So 5.5.
What would you think?
There you
Oh,
go.
we're going days.
That's a great sign.
Thank you, Tom, for connecting.
5.
Oh, 5.5 what, Tom?
Oh,
5.5
we gotta
what?
label. We gotta label.
Yeah, label.
We can't get the half-lives.
There you go.
Half-lives.
Guess who's gonna be wondering about us? Alright. Alright, so questions on 8 or 9? Alright, so now we have a decrease in radon concentration in Tony's grandparents' house is an example of exponential decay. Exponential decay can be modeled using an exponential function. In exponential decay, a quantity is multiplied by a constant factor that is greater than 0 but less than 1 during each period. So 10a, the concentration of radon is multiplied by a constant factor for each half-life. So what's our constant factor? Half. So write an exponential function, r of t, for the table in item 4, using 400 as the initial concentration of radon and a constant factor from part A. So what would our equation be? If we were to write this out, using what we know for exponential growth, we take our first term, which is what we start with. So we start with 400. And what are we multiplying by each time? Half. And then to t. So with an exponential function, our variable is in the exponent. All right, so in your groups, let's look at number 11 through 17. So we're going to use the equation we just built. So identify the meaning of RT and T. What are reasonable domain and range? All right, so when we're looking at domain, what are we looking for? What domain is that, input or output? input, right? So reasonable domain. So we can say any number, right? But are we ever going to have more than 400 PCI per liter? No, because that's what we start with, right? And over time, since we've removed the source, it's going to decrease, right? So our domain T is time, right? So our domain is T. Can we go back in time? No. Once we've removed the source, so time, what's our smallest time going to be? 0. So we're going to take 0, and T is going to be greater than or less than 0. Greater than, so we're going to have 0 is greater than, or no, you're right. So T is going to be greater than or equal to 0. Perfect. And then for our range is our RT. So it's our amount of radon. So our range, how does that compare to 400? So more or less? Less than 400, right? But never 0. So we're going to go between 0 and 400, and that's going to be our radon amount. Unless she doesn't have to.
Or she has.
You got feeling right.
All right. All right. So are we okay with where our range is coming from and our domain? Well, it's coming to.
Wow. Snow is coming, guys.
Well, it's not.
Yes, it's gonna be snow. Hopefully, that'd be awesome.
All right. So
I know.
number 12, describe how your answering number 10A is related to the function RT. So how is our answer? So our range here, how does that relate to our situation? Why are we never going to have 0? How come we're never going to have 0? Right. So at some point, even though it'll be untraceable, technically the particles are always there because it's decreasing in half, right? And if you have something, can you cut it in half, even if it's minute? Yep. What's minute? The amount of radon. Right? Because you cut it in half, you have 12.5, and then you can cut that in half, right? And then you can cut that in half, and you can cut that in half, and you can cut that in half, right? Even if you have 1,000th of a particle, you can still cut that in half, right? Yep. Alright, so, and that's where, this is coming into play when we take medicines. Technically, the medicines that we take are never completely out of our system because our bodies break them down, but they have half-lives, and, they're never completely out of our systems. So, forever and ever. So we did that. So number 13, did anybody graph it and want to share the graph? So this is kind of like what we had earlier, but now, so at 0 we had 400, right? And then at 2, at 1 half-life we had 200, and at 2 half-lives, and then 3 half-lives, and then 4 half-lives, and then 5 half-lives, 6 half-lives, 7, 8. We're going to keep on getting closer and closer to 0, but are we ever going to get there? No.
It's gonna be really, really small.
So how is the original concentration of radon related to the function? It's our starting point, and is it our max or min? It's our maximum amount, right? function to identify the concentration of radon after 20 days. So our function we had before was R of T equals 400 times 1/2 to the T, where T was the number of half-lives. So if it's at 20 days, how many half-lives is that? 5, so we're going to put 5 in for T. How could we tweak that equation so that instead of putting the number of half-lives, we could put the number of days? Well, if I give you 20 days, how do you figure out how many half-lives that is? Divide by 4. So what could we do with our T? To make this instead of the number of half-lives, if I say I want that to be days, divided by 4. So now instead of putting in the number of half-lives, we can put in the number of days. So if we put 20 days in for here, it equals the same thing. And so we get, how much is it? 50? 20, is it 25 for this amount? If R equals 20 days.
25.
Right, so if we get 22 days, that's 4.5 half-life. So if we put 22 in for days, what's 400 times 1/2 to the 22 divided by 4? What is it? Right, so at 22, so if we put, so you're doing number of half-lives, so you're putting, instead of doing T over 4, you're putting half of the number of half-lives, right? So, what do you get for that one? What's the amount? For 22 at 9 point something? So it's 9.375. Alright, so now will the concentration of radon ever be 0? No. It will get close to 0, but can we take a number? What's the only number that when we multiply by half we get 0? 0, right? So are we ever going to have 0 amount? Are we ever going to be taking 0 times 0.5 or times 1.5? 0.5? No. Because we're always going to get some fraction, right? All right. Questions?
R will be 8.3.
I roll like this 22,
16.
24.
Alright. So your homework is going to be the practice. So 20 through 24. Let me double check this one. You're right.
Take my book back. Cool, you should dig her. I get your book yesterday. We're taking my book
You
back.
don't have to.